Okay.
Okay, so let us begin. Magnetics, we have discussed it. Okay, let me just review one thing, that suppose in a circuit, you have a circuit, okay? Suppose this is a circuit, we have a circuit, suppose, okay, suppose this is a circuit and there is a like a bulb in the circuit, and of course, um, suppose a bulb, red color bulb in the circuit, and the circuit has a battery, of course. So draw the battery. Suppose here is the battery. Okay, suppose here is the battery, positive, negative. Now of course we know, suppose this is a bulb in the circuit. Okay, so here here we can say the current will move from positive side and go through over the circuit and come to the negative side, right? Right, so in a circuit it happens that charge moves from battery's positive side and goes to the negative side. It is a common nature of the circuit, which and a moving current, and the current is moving, of course. So here we call this current moving current. Of course the current is moving from one point to another, from a circuit's one point to another, the current is moving. But the situation here is that here we're going to discuss about the magnetism in a moving current, or a moving current. When current is flowing through a circuit, something special happens. What is that? It creates magnetism property in a moving current in the circuit. The point where the current is moving, every point throughout the moving current, or we can say every point in the circuit, there's a situation where magnetism happens, or magnetism property happens. That means magnetic field line occurs. So we can show the magnetic field lines something like this way. It has multiple lines, so something like this is occurring. Okay, and it is happening every point in the circuit. It is happening every point in the circuit where the current is moving, of course. If that point doesn't have a moving current, it cannot create this magnetic field right here that we are showing. So the main concept in this here is that a moving current in a circuit creates magnetic field line, and this is the shape of the magnetic field line that in a circuit we see happening. So that's what we discuss here, and we also discuss the direction of the magnetic field line. Of course it is moving in a circle, but it is anti-clockwise or clockwise. That means if it is moving in this direction, or in this direction. The way to find out about the direction is the right hand rule. We already discussed about it. So the right hand rule, we have to focus on this part right here. The right hand rule, the thumb's direction is considered as the current direction, and the finger right here, the finger's direction is considered as the magnetic field's direction. So if we compare this, let's say we take this line here. Okay, we take this line here, and if we consider it, and of course we have to rotate it because current direction is now downwards, right?
Yes.
So if we compare this, see what is happening. The current direction is this way, right? This is the current direction. And where is the
May you repeat it, sir?
okay, you have understand the magnetic field which is generating because of the moving current, right?
Yeah.
Okay, now we are discussing about the magnetic field's direction. Since it is moving in a circle, right, in a moving circle path, right, that we
Yeah.
show in this figure. So it could be in clockwise direction or anti-clockwise direction, right? These two things can
Yeah.
happen. In a circle, which direction? Can you say left, right in a circle? Of course not. You have to say
No.
it's moving in a circle clockwise or anti-clockwise. That's how you get the direction idea in a circle, right? So
Yeah.
if we consider that theory, or if we understand that theory, then we have to understand that to find the magnetic field's direction, we need a rule, and that rule is called the right thumb rule, right? Right
Yes.
thumb rule, which is in the book, you see. Okay, thumb rule. So here we have to take our right hand, and the thumb's direction, see, the thumb's direction is downwards now, right? Because I rotate the
Yeah.
picture.
Hmm.
So, and also we are matching the direction right here with the current's direction, right? See, downwards, right?
Yeah.
So if we turn our thumb in downward direction, where the fingers are moving, is it moving in clockwise or anti-clockwise? See, if you can do this example with your hand also. If you move your hand downwards, sorry, thumb in downwards, okay, take the
Hmm.
right hand,
Okay.
and like turn the thumb in downwards direction. See where the fingers direction is. Is it in clockwise direction or the anti-clockwise?
Okay. So I have my right thumb, and it's in
Hmm?
anti. No,
And
it's in
clockwise, right?
anti.
Yeah,
Hmm.
anti
It's in clockwise.
clockwise. Do you understand why is it clockwise, right? Because if you
Yeah.
move the thumb in downwards, the fingers are moving in a clockwise direction, right? So that
Yeah.
clockwise direction is the we can say is the same as the magnetic field's direction, because the finger's direction is compared to the magnetic field's direction. So that's how we get the idea where the rest of the magnetic field's direction will be. So all will be clockwise, that means in this direction, right?
Yeah.
Okay, so we have got an idea about the direction. Now we're gonna discuss about the solenoid. Okay, let's go to the solenoid. So in solenoid, first of all, what is solenoid? If you want to give a definition, the definition is in the book, of course. Here is the definition. Um, Here is the definition. You can increase the strength of the magnetic field that a wire produce by wrapping the wire into a coil called solenoid. That means solenoid is the wrapping wires into a coil in a circuit, that is called solenoid, right? So if we wrap the wire, well, that means we're wrapping the wire, that means we're creating loops, right? Loops of wire.
Yes.
Okay, so that's
Yeah.
what we call solenoid. So basically solenoid is the making loops with wire, or we can say making coils of wire, right?
Yeah. Hmm.
So we're creating loop where? In the circuit, right? In the circuit, we're creating loops of wire. Why? What's the advantage of solenoid? Why we need solenoid? Simple. To increase the strength of the magnetic field, right? To increase the strength
Yeah.
of the magnetic field. We know when a current moves in a circuit, it already creates a magnetic field, right?
Yes.
But can you increase this magnetic field somehow? Yes, you can. What is the way? We have to create loops of wire. That means what we call this loop of wire or coils of wire, it's called solenoid. That means we need solenoid process. That means creating loops with wire in order to increase this magnetic strength, right? So
Yeah.
solenoid's basic advantage or basic reason why we use solenoid in a circuit is to increase the magnetic field. That's the main and not only reason but the main reason, of course. So it has a lot of advantage, and we can increase this magnetic field even more if we make more loops or more coils of wire in the circuit. That means the more you create coils of wire, that means more loops are created, the magnetic field will be increased more. So what is happening inside the solenoid, we have to understand with this picture right here. So if we take this picture and discuss it again, we have discussed it already, but let's do it one more time. So what happens in this picture, you can see there are some magnetic field lines which are curved and some magnetic field lines which are straight, right, or uniform. So
Mm.
there are two types of magnetic field line here in the figure, or in a solenoid we can say. First of all, there are two types of magnetic field line. Two types of magnetic field line. We are calling these lines magnetic field line, right?
Mm.
Okay, so there are two types of magnetic field line. One is the one that is being curved, or we can say the first one is the uniform field line. Okay, first we call the uniform. First we write the uniform field line, or uniform magnetic field line we can say. So I'm writing in short, magnetic field line, MFL, magnetic field line. Okay.
Okay.
Number two is the line which are curved. That means curve magnetic field line, same as MFL, magnetic field line. That means some are uniform and some are curved. Where are the uniform magnetic field line? Where are the uniform, or we can say straight or even, right?
Mm.
Where the uniform magnetic field lines are in the picture?
Sorry, just hold.
Okay, so where are the uniform uh, field line in the picture?
Pardon, sir?
Where the uniform magnetic field lines are?
Inside of the solenoid. Sir?
Yes, inside the
It's inside the
solenoid.
solenoid.
Yes,
Inside
of
the
course,
solenoid.
yes. That means this portion right here, right? These line
Yes.
here that are going inside the solenoid, right?
Mm.
So these line here inside the solenoid are called uniform magnetic field line. And where are the curved magnetic field line? And of course, remember the curved magnetic field line is same as the magnet's field line. We have seen in magnet that the figure right here which has been curved, right,
Mm.
the same as a magnet, same as a magnets, magnets magnetic field line, same as magnets, magnetic field line. Because if you see a magnet, of course a bar magnet, right? So
Yes.
if you take a bar magnet and see its magnetic field line, see it's same as the curved field line in the solenoid, right? See how it goes, right?
Hmm.
So we compare it with a bar magnet's magnetic field line, the curved field line, okay?
Okay.
So here you can say there are curved field line in the upward and downward direction, right? In here and upwards or outside, right? Outside the solenoid, right? You can say. So
Hmm.
where is its location? Outside, right? Outside the solenoid, or we can say outside in short, right? And where is the location of uniform? Inside, right?
Yes.
So one is inside, one is outside, and one is this is being compared with the bar magnet's magnetic field line because it's the same, right?
Yes.
Okay, so that's what we got from here. That's the understanding here. And let's see if they have add any of them. Okay, yes. Okay, now read these 3 points right here. Not this one. I will discuss it. 6 and 7. Okay, six is important. And of course, remember how long. Now another question: how long this solenoid will be present in this? Uh, we can say how long the magnetic field will be present in the solenoid. How long the magnetic field will be present in the solenoid? That's another important question because this magnetic field's duration is dependent on something. And what's that?
Pardon, sir?
Okay, let me ask you a question, which is that here you can see there is magnetic field, right?
Mag.
Magnetic field in
Yes.
the solenoid, right? We have discussed it in details. So what's the time, or we can say what's the duration time? Duration, what is the duration of this magnetic magnetics magnetic field line here? Is this have a time limit, or is it dependent on anything, or is it
Well, it is. Well, if it's like a machine, then like an on and off switch would be dependent.
no, of course on a source switch is dependent, but there is another key important elements that needs to be present in this situation in order for the solenoid to have the magnetic field. So what's the key element here?
Um. Is probably the bar of metal that's inside.
No, that was a bottom. There is a electro magnet, we'll say later, but that's not the topic here. It's dependent on the current, of course. Remember, it's dependent on the current, because if current is not present, nothing will be, no magnetic field will be created, right? Because in a circuit, in a wire, how the magnetic field is created? Because of the moving current, right? So if the current is not flowing through the solenoid, no magnetic field will be produced and no situation will be created, right?
Hmm.
So of course the main key element here is the current, a moving current, of course, which is flowing through the circuit, right? Or flowing through the solenoid, of course. So if the current is not present and the current is not flowing inside the solenoid, it cannot create magnetic field line or any magnetism property in the solenoid, right?
Yes.
So current is the key element here. Current, remember it,
Current. Oh yeah.
right? Didn't you
Mhm.
understand? I discussed it like, okay.
Okay. Yes.
So current is the key element here. Now, let's. Okay, I think we're done with solenoid. Electromagnet. Next comes electromagnets. Okay, next comes electromagnet. So what is electromagnet? Do you remember, or read this line if you don't?
What do you need?
Okay, so what is electromagnet?
Sorry, sir. May you repeat it?
Okay, what is electromagnet?
Electromagnet.
Yes, electromagnet.
It's a. It's a metal. It's a metal object in a solenoid.
Inside, yeah, a solenoid with an iron core, right?
Oh
It's
yes,
called,
with an iron.
yeah. So a iron core should be present inside the solenoid, right? Or
Yes.
we can say the solenoid will be wrapped around the iron core, right?
Mm-hmm.
So it will create what? Electromagnet.
Like magnet.
Yes.
Oh, yes.
Okay, so now comes what's the use of electromagnet? Okay, now comes the what's the use of electromagnet? Electromagnet can be used in order to the increase the value of the magnetic field or increase the power, right? We need to use the electromagnet. So how we create it, we already know it, but do you understand this mechanism here, this circuit or this topic here, the uses of electromagnet?
Yes.
Okay, should I discuss it?
Yes. Just make sure.
Okay, so firstly we can say there are two circuit here, right? One has electromagnet and of course a battery switch, and it is contact with a iron contact. That means that iron is present on top with the rocker. Rocker is an element that can move like a seesaw, we can say. Okay, like a seesaw in the park, right? It will move up and down, something like this way. So rocker is an element which moves up and down, and here we can see the pivot is the joining point of the two rocker, we can say. So pivot is the middle point that we see in a seesaw, same thing. So the joining point of the rocker is called the pivot. So here pivot is connected to another rocker downwards here, and this rocker is connected with a switch which is on the second circuit here, and second circuit has a motor, of course. Okay, so what's the understanding here? The understanding is that when the circuit is turned on the first circuit, when the circuit is completed, or we turn on the switch, the battery is connected with the solenoid and the iron core. That means electromagnet will be turned on, which will be creating more magnetic field than the original circuit have. That means the magnetic field will be increased, and this will come in contact with the iron contact here, which is connected with the rocker. For the rocker will move downwards, and if the rocker is moved downwards, the connection with the pivot with the second rocker will be moved to the right. which will complete the second circuit. The second circuit switch will be on and making the motor turn on. That's what the main mechanism right here. Okay.
Okay.
So dependent on the first circuits turning on the switch, we activate the electromagnet, which is creating lots of magnetic field and activating iron contact with the first rocker, which is connected with the pivot with the second rocker on downwards, and the second rocker moves right to make the
Yeah.
contact of the second circuit and turning on the motor. So basically the end goal of this process is to turn on the motor, but how? We need to complete the first circuit. That's how. So in
Okay.
a machine you will see there are situations where we need more magnetic field to process or turn on the motor, that we can see. So this mechanism or this process is used in this kind of machine. It may use on a pump in fields that the farmers use. There is a lot of pumps and motor, right, that is used in the field. And we can also use in our daily life. Maybe lots of pumps are used in our home also to get water from the tank, right? So this kind of situation we use motor to do work, heavy load work, right? So
Yeah.
in this situation we need this kind of mechanism to turn on the motor, and this mechanism is quite efficient because motor needs a lot of power and lots of mechanical force to turn on, right? So this kind of situation is needed in order to turn on, because if you do manually, that means you're doing hand labor to turn on the motor, it may take a lot of energy. Maybe sometimes it will turn on, maybe sometimes it will not. You have to create a lot of energy to turn on the motor. That may you that you will not see in various situation. So this helps you in order to turning on the motor and of course doing your daily work that you need with the motor. So this situation is needed in order to do various kind of work. And of course field around the electromagnets and bar magnet are the same shape. Yes, the fields around the electromagnet, this situation is also a good lesson here. So read this lesson and tell me if you understand or not. The field around the electromagnet and the bar magnet are the same shape. You understand this?
Yes.
Okay, so what will be the figure? Can you draw it and send it to me for electromagnets magnetic field?
Hmm.
Electromagnets magnetic field, can you draw it?
So can I draw an electromagnet?
Yeah, you have to draw first of all electromagnet, then the electronic field of that, right?
Oh yeah. Okay.
Okay, so do it and let me see the picture. Okay, so are you done?
Almost, sir. Okay, yes, I have sent it, and I challenged myself like not really to look at it, so I like memorized it.
Okay. Okay, so let's see the picture right here. Yes. So this is the iron core, right? And this is the
Yeah.
solenoid that we wrapped around the iron core, right? Okay.
Yeah.
So yeah, it's same as the bar magnet, but you have to join them, right? Something like this. Figure should be something like this. Okay, it's same as the figure as the bar magnets figure. Okay, so something like this. See, this is the figure, complete figure. Okay,
Oh, okay.
same as the bar magnet. They say in the statement right here, same as the bar magnets field, right? Bar magnets field is how.
Bar magnet field.
Yeah, bar magnets field is what is the figure for bar magnets field? Is
What figure?
is this figure right here? This is the figure, right? This figure right here on the right
Where?
side.
Where? Oh yeah, yes, this one.
Yeah, so
Wait,
it's
so a magnet kind of acts like a solenoid with an iron core.
yeah, that's the topic, whole topic we discussed in the whole lesson, right?
Okay. Yeah. Yeah.
Okay, you have understand right now, right?
Yes.
Okay, so yes, it's acts like a bar magnet, same thing. So basically, this is a magnet in some sense, right? and solenoid is
Yeah.
also same, a magnet. Basically it turns magnet how? When current is flowing, right? So when the current is
Yeah.
flowing, it turns into a magnet. As simple as that. The anything that has a magnetic field is a magnet. Anything that has a magnetic field is a magnet, right? So that's the observation here. Okay, so we have discussed uh, all the topics. Do you have any question, any other question?
No.
Okay, should we conclude the class?
Yes.
Okay, so learn the Maggie field. I'll take the test tomorrow, right? We have a class on tomorrow or on Monday? What's the date?
No, we have it on tomorrow.
Tomorrow. Okay, so I'll take the exam and then we will learn about any other lesson that we want to. But the class has start, right, in your school?
Not yet.
Okay, so we can learn any other topic or any topic you prefer on the next class. Okay, so let me know when what topic should we learn next, and we'll take the exam. Okay, we are done for
Okay
today.
then.
Thank you
Thank
very
you very
much.
much, sir.
Walaikum assalam.